Basic concept of substitution and elimination reaction. Nature of chemical reaction. If you carefully analyze the type of chemical reaction which are observed in organic reaction is mainly of four types. First, substitution. Second, elimination reaction. Third, addition reaction. And last one is the rearrangement reaction. It means whole organic chemistry only have these four type of chemical reaction. One in the form of substitution, second elimination, third addition, or fourth rearrangement. What is the meaning of substitution reaction? If organic compound have A, B, when react with C and give A, C and B goes out. That means when old sigma bond is broken by a reagent C and a new sigma bond is formed and something goes out, that particular part is called as leaving group. In substitution, in all substitution reaction, old sigma bond are broken by a reagent and a new sigma bond is formed and leaving group goes out. Such reaction is called as substitution reaction. In all cases, there is breaking of sigma bond and formation of new sigma bond. Such reaction is called as substitution reaction. Elimination. The meaning of elimination is A, B, C, D when react with any reagent give A double bond B, C, D. That means old sigma bonds are broken and corresponding a new pi bond are formed. Such reaction is called as elimination reaction. CD is the leaving group. That is, in all the cases there is breaking of sigma bond. Here these two sigma bonds are broken and there is a formation of multiple bond. So in all the cases there is breaking of sigma bond and formation of new multiple bond. Addition reaction. A double bond B when react with CD, A, B along with CD is formed. A, B have multiple bonding, react with reagent C, D and corresponding sigma bonds are formed. That is, in all cases there is breaking of pi bond and formation of new sigma bonds. Such reactions are called as addition reaction. What is the meaning of rearrangement? If substrate have A, B, C when react with any reagent and if you got A, C, D where substrate have attachment where V is attached to A and C, but in product here B is attached to C. That means in all the cases there is difference in attachment of atoms by either hydride, methyl, phenyl or bond shift. Now journey of substitution elimination reaction. Nature of substrate. Here I have taken different methyl halides. Here methyl is common in all the cases. In first case fluorine, second chlorine, third bromine and last one have iodine as a leaving group. When you look about over the electronic size, this white part is the hydrogen, this one is carbon and this particular green part is the halogen. The size of methyl fluoride is this one, size of methyl chloride, here size of methyl bromide and here size of methyl iodide. You can think about the bulk in case of methyl iodide. In different alkyl bromides, here I have taken same leaving group bromine but changing different alkyl groups. In first case CH3, second ethyl, third isopropyl and fourth one is the tertiary butyl part. Look about the size. This is bromine hydrogen hydrogen, here 1 methyl group, here 2 methyl, here 3 methyl. Molecule have this much bulk over the carbon. Different tertiary butyl halides. Here I am changing halogens with tertiary butyl groups. First is fluorine, second chlorine, third bromine, and lastly iodine. Size is nearly same because all are of 2p orbitals, but here size of chlorine is larger, bromine is much larger, and iodine it is highest. Nature of reagent and different nucleophiles. Nucleophile for SN1 reactions are generally water and alcohol, but if alcohol is there, then think for the size of alkyl group. This white part is hydrogen and red part is oxygen. This is the shape of water, methanol, ethanol, isopropanol, and tertiary butanol. You can think about the steric factor in butanol. That's why this butanol rarely acts as a base, rarely acts as a nucleophile. It always acts as a base. But water and methanol acts as a nucleophile and attack over the carbon. But tertiary butyl alcohol act as a base only and abstract proton instead of attacking over the carbocation. Nature of SN1 reaction. In all the SN1 reactions, first leaving group goes out, form carbocation, and this water attack over this carbocation and form overall alcohol as a product. So SN1 reaction comprises in 2 steps. In first, ionization or solubilisis take place, and second step, water attack as a nucleophile loses water to form alcohol as a product. You can see the potential energy, you can see the energy as well as size of the groups. Here this particular is bromine. Due to steric factor over this carbon, no nucleophile directly attack over this part. Therefore first Br goes out, carbocation is formed, which is planar in shape. Now water attack over this part to form alcohol as a product. I will discuss energy diagram later on. In terms of stereochemistry, this carbocation is planar in nature. Therefore nucleophile may attack from the top or from the bottom to form alcohol. If this particular carbon is chiral in nature, then racemic mixture will be formed as a product, which may attach from this position or may attach from this position. SN1 reaction. You always think for a perfect substrate for SN1 reaction, and the perfect substrate is tertiary butyl bromide. The size of tertiary butyl bromide in ballistic model is this one. This part is bromine, CH3, CH3, CH3 attached to this carbon. Fastest for tertiary substrate, that is SN1 reaction is highest for tertiary groups, tertiary alkyl part, because of steric factor. Need a non-basic nucleophile, that is a weak nucleophile. I am using non-basic because if a good base is there, that it may abstract proton to give elimination reaction also. In all the cases you have to break this carbon halogen bond, therefore a good leaving group is there, and as carbocation is formed as a product and nucleophile attack over it, therefore racemic mixture is formed because nucleophile may attack from top or from the bottom. SN1 reaction depends mainly on 2 factors, that is reactivity depends mainly on steric factor and the stability of carbocation. You can think the steric factor over this carbon, greater is the steric over this carbon, higher will be the reactivity, and second stability of carbocation. Remove this Br and form the carbocation. Greater the stability of carbocation, faster will be the rate of reaction. Look for the video complete SN1 reaction.
Tertiary halogenoalkanes undergo SN1 reactions, where S indicates a substitution reaction is occurring, N indicates that a nucleophile is involved, and 1 indicates that only one species is involved in the slowest rate-determining step. In tertiary halogenoalkanes, the small hydrogen atoms in primary halogenoalkanes are replaced by bulkier alkyl groups. Tertiary halogenoalkanes. The bulky alkyl groups do not allow attacking species to approach the central carbon atom. Consider the reaction between 2-methyl-2-bromopropane and a hydroxide ion. It has a two-step enthalpy profile. The first step, the heterolytic fission of the carbon-bromine bond, has a high activation energy, EA1, and therefore determines the rate of the reaction. The first step involves only the halogenoalkane and proceeds via a transition state complex to form a carbocation. The second step has a much lower activation energy, EA2, and hence is considerably faster than the first step. The carbocation reacts with a nucleophilic hydroxide ion via a second transition state to form the product 2-methyl-propan-2-ol. Transition state, carbocation, EA2.
Now, for SN2 reaction. Here, make the perfect substrate. This is methyl bromide. Size of methyl bromide is like this. This carbon have 3 hydrogen, 1 bromine. The size of bromine is very large. Therefore, nucleophile may not attack from this side. So attack from the back side of bromine. It is fastest for primary substrate. Need a non-basic nucleophile, and that nucleophile must be strong, because nucleophile have to break this particular carbon halogen bond. So must have a good strength so as to break it. In this case also, carbon halogen bond must be broken. Therefore, a good leaving group is there. Nucleophile attack from the back side, forming a transition state. Therefore, if this carbon have different groups, so inversion in configuration is observed, and this inversion was first reported by Walden. It is also called as Walden inversion, which is observed in SN2 reaction. Reactivity depends on 2 factors here again: steric factor over this carbon and electronic factor also over this carbon. That is, reactivity depends on minimum steric and maximum positive over the carbon directly attached to halogen. In this case, you have to think about the steric factor over this carbon as well as electronic factor over this carbon. But in SN1 reaction, you have to think steric factor over this carbon but electronic factor over the carbocation. In SN2 reaction, why steric factor is important? You can see in this case, this is methyl bromide. Nucleophile attack from the back side, as no space is there. No space is there to attack from this side. When you increase the size by replacing hydrogen with CH3, in case of ethyl bromide, you can also see the steric factor again. So no nucleophile attack from this side. Here again nucleophile attack from the back side. As you increase the steric hindrance over this carbon, by changing two hydrogen with methyl group. In case of isopropyl bromide, steric factor increases. Attack of nucleophile over this position is decreasing slowly. In case of tertiary butyl halide, where all the hydrogen is replaced with CH3 group, there is no place for a nucleophile to attack over this position. Therefore, in case of tertiary butyl bromide, SN2 reaction is very less. This is the best substrate for SN1 reaction. I have told in SN2 reaction, inversion in configuration is observed. Thus, inversion means R to S or S to R. It is not always so. It depends on nature of reaction. It depends on the substituent priority. In case of alkyl halide, this carbon is attached to alkyl group as well as halogens, and nucleophile attack from this position, and nucleophile may be of oxygen, nitrogen or another halogen. All have priority higher than this carbon. Therefore, inversion in configuration is observed. But if any valency is other than carbon, here oxygen, so there is possibility that S may retain its configuration. So it is important. In case of only alkyl halide, R give S, but in case of substituted alkyl halide, there is possibility that S give S or R give R. Complete SN2 reaction.
Primary halogen alkanes undergo SN2 reactions, where the S denotes a substitution reaction. The N shows the reaction involves a nucleophile. 2 is the number of species involved in the slowest rate-determining step. A nucleophile is an electron-paired donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromomethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom, because the bromine atom A is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released. The transition state complex.
Now SN2 reaction completed. Now even reaction. In case of even reaction with the perfect substrate, it is the tertiary butyl bromide. Size of tertiary butyl bromide is this one. It has very much steric hindrance. Fastest for tertiary groups or tertiary substrates, because elimination depends on the stability of product, and if it is tertiary in nature, then more hyperconjugation and inductive effect is there in case of alkene. Need a weak base, because in even reaction first halogen goes out, carbocation is formed, and base abstract proton from this position to form double bond, and rate depends in first step, that is formation of carbocation. Therefore, a weak base is present in even reaction. In even reaction also, you have to remove leaving group. Therefore, a good leaving group must be there. Product will be more stable alkene. As I told you, elimination means stability of product. Reactivity depends here again on the basis of two factors: maximum steric over the carbon which have attachment of halogen and stability of carbocation. In E2 reaction, substrate is same as that of E1 reaction, that is tertiary butyl bromide. You can see the steric factor again. As I told you earlier, that elimination means stability of product. So E2 reaction is also fastest for tertiary substrate, whether reaction is E1 or E2. Both depends on the stability of product. The difference is only in the nature of base. In UT reaction, strong base, alkoxides are generally used, and this alkoxide generally started from ethoxide onward. Here again a good leaving group is there, because you have to remove leaving group. Product will be more stable alkene, as I told you. Here reactivity depends again on the steric factor and the maximum partial positive charge over the carbon. I have made a chart for the comparison of substitution and elimination reaction. Reaction: structure of alkyl halide, reactivity of nucleophile, concentration of nucleophile, solvent and stereochemistry. I am discussing one by one. In case of SN1 reaction, nature of alkyl halide is tertiary, higher than secondary, greater than primary. And for SN1 reaction, most likely substrate is the tertiary alkyl halide, as carbocation is stable and it has greater steric factor, greater steric hindrance over the carbon, which is directly attached to halogen. As I told you, reaction proceeds in two steps. First, halogen goes out to form carbocation, and now nucleophile attack over that carbocation to form overall product. Therefore, weak nucleophiles favor the reaction, and that nucleophile is generally water and methanol. No effect of concentration of nucleophile, because nucleophile attack in the second step, second fastest step. Polar protic solvents favor the reaction, because the carbocation as well as halide, which is formed after first step, are stabilized by the polar solvent, polar protic solvents. If water is there, then lone pair of oxygen stabilizes carbocation, while partial positive charge over the hydrogen stabilizes halides. In terms of stereochemistry, racemization with some more amount of inverted product is observed in SN1 reaction, but important part is the racemization. In case of SN2 reaction, as I told you, steric factor and electronic factor, greater the steric hindrance, no nucleophile can attack over the carbon which is directly attached to halogen. So for SN2 reaction, general order is the primary greater than secondary is greater than tertiary, that is most likely to react with the primary alkyl halide. For reactivity of nucleophile, strong nucleophile favors the reaction, because nucleophile have to break carbon halogen bond. Concentration of nucleophile, high concentration of nucleophile favor the reaction, as nucleophile again have to break the carbon halogen bond. When you see the solvents, solvents are generally polar aprotic, because polar solvent is needed because alkyl halide or substrate is polar. But if you use polar protic solvent, that it will favor the ionization of carbon halogen bond. Therefore, a polar aprotic solvent are used. In terms of stereochemistry, inversion in configuration in case of normal alkyl halide. Here nucleophile attack from the back side to form overall product. In E1 reaction, as I told you, whether reaction is E1 or E2, stability of product is the main factor behind elimination. Therefore, substrate for E1 is tertiary, followed by secondary, followed by primary in reactivity. That is, tertiary is more reactive and most likely to react with the alkyl halide are the tertiary groups, tertiary alkyl halide. Reactivity of nucleophiles or base, weak base favors the reaction. Here the bases are generally ethanol, propanol, isopropanol. Concentration of nucleophile, as reaction occurs in two steps. In first, ionization and formation of carbocation occur, which is rate determining, and second, base abstract proton to form alkene. And second step is fast, so no effect of concentration of base. In case of solvent, alcohol are polar in nature, therefore polar protic solvents favor the reaction. In terms of stereochemistry, more stable alkene will be the major product. That is, if cis and trans are formed, then trans will be the major one because of its stability. In case of E2 reaction, substrate is again tertiary, followed by secondary, followed by primary, because again for the stability factor. In case of E2 reaction, nucleophile have to break carbon hydrogen bond as well as carbon halogen bond. Therefore, strong nucleophile, strong base is there, and these bases are alkoxides. In concentration of nucleophile, high concentration of base favors the reaction. And in terms of solvent, polar aprotic solvent favors the reaction. And in terms of stereochemistry, again similar to E1 reaction, more stable alkene will be the major products. That is, if there is comparison of trans and cis, then trans will be the major product in E2 reaction.